went on Blackboard and it was there.
But you're not registered in my class. You're not showing up in the roster.
How do I do that?
Did you take the course code notes?
Yeah, but I didn't know where to put it in.
Because it's like, it should be back when you sign up for classes. Okay, well, let's look after class, because we got to add you, because you're not showing up on my Blackboard at all. So you have access to the Blackboard? The full shell, the lecture one? Because I have 3 different shells, but I only use the lecture shell. So you should look if you have lab or recitation, because I don't actually put anything in there, just the syllabus. But in my shell, my main shell when I was checking, you were not there. So that's why.
Yeah, I have no idea.
Okay, yeah, we got to talk after class, though, for sure, because we got to get you signed up. I think we still have 2 minutes till we officially start. We can go ahead and start getting your brains fired up. Oh, okay. Yeah, otherwise I think I can remember, but I need to redo that. What's your name? Okay, does someone want to start putting the first one somewhere on the board for us? Maybe that far board, the 2.5 meters to millimeters. Did you have your hand up over there? Sweet. Yeah, write us the whole step, walk us through. Uh-oh. Hopefully we have functional markers. So that looks good. Although, did you put one too many zeros? So the work looks good. So we have, right, our conversion factor. Right, so this is just your conversion factor that you ideally pulled from that little cheat sheet. And then just plug it into our calculator. There's 2,500 millimeters. Questions about that? All right, who wants to do the next one? So 4.5 centimeters to kilometers. This could be a trickier one. A lot of different tricks to get there. Yeah, go for it. If you get it wrong, there's no shame. No one else is volunteering. So it looks like we're doing a two-step conversion, so that would be my advice. Oh, I think your conversion factor is a little off, though. Eh. No, it's fine. As soon as you get to the board. So yeah, there's our relationship, right? So it's just how many centimeters are in a meter. That's our conversion factor. Centimeters is on bottom since we're canceling that out. You can see centimeters cancels. So you can do centimeters to meters to kilometers. And so that looks like a good conversion factor for the kilometer. So kilometers on top, 1,000 meters on bottom. Excellent. So then we get 4.5 times 10 to the negative fifth. Anybody do that a different way? So what did y'all do?
Just move the decimal point for.
So let's kind of think about that. So, right, you're saying, so centimeters, so again, this is by the base unit. So centimeters is 10 to the negative 2, kilometers is 10 to the third. And so again, if you don't see this, it's fine, but you might see, oh, this is, right, a 10 to the fifth difference. So you could subtract them, right, to get the difference. So 3 minus a negative 2 gives us a 10 to the fifth difference there. And so that's where you could say you move the decimal point over, or you could write your new conversion factor between the two. And so know that centimeters is the smaller one, so that means that there must be 1 times 10 to the fifth small things in the large things based upon, again, the exponent. So that would be another way, and again, you get the same answer. And of course, you could do the decimal moving thing, but like I said, I always get squirrely if I look at too many zeros. I'd rather do the subtraction. Excellent. All right, let's try the next one. Any brave soul want to put this one up there? The meters to decimeters. Decimeters is just an awkward one. We don't use it too much. Who wants to go for it? Man, no volunteers? Nobody wants me to start picking on people. I also don't have my roster in front of my face. If I could get it. / I only remember some of you. Bianca, do you want to go for it? No, why not? If you don't know it, then somebody else doesn't know it, and we could all go through it together. Why is the decimeter one so tricky? This should be an easy one.
Because I wrote it as decigrams.
It doesn't matter. So what's the deci factor, though? So how many decigrams are in a gram, then? 10. So, right, if there's 10 decigrams in 1 gram, well, let's do the same thing for meters, right? There's 10 decimeters in 1 meter. Now we can go from there, right? There's our conversion factor. So hopefully that's what you have written on your sheet. So then we'll just set up the dimensional analysis. Yep. You can't let the weird things. And so on an exam, right, I might not give you real conversion factors. So I might give you a conversion factor, you know, how many blips in a blop or whatever. You just got to go for it, right? You just got to know your unit conversions, how to set it up. Does anyone want to try this next one? Decimeters to millimeters. Put it on the board for us. And this one, you can even treat it, right, as a two-step process if that's confusing, right, to go directly from decimeters to millimeters. You can still go decimeters to meters to millimeters if that helps you. So it's all your comfort. Someone want to put this one on the board? You want to go for it? I think you're a little off on your.
I don't know if I wrote that right, yeah.
Yeah. So.
Do I flip these?
So yeah, there's something funny. So there's two funny things. So what's the deci exponent?
Meter? Right?
Well, what's it by the base unit though, meters?
The -1,
So to the -1, and what's millimeters?
-3.
So right there's 100 difference between them.
Oh.
So there's 10 millimeters and a centimeter. That would be correct. Yeah. So that looks better. So now 100 millimeters and a decimeter. But right now our math doesn't match up, right?
Where?
So the units have to cancel?
Yeah.
So you gotta flip it. So millimeters on top, decimeters on bottom. Yep. And so that was tricky. So if you didn't follow that, let's look at another way to do that. So, right, this may not be so obvious that there's 100 millimeters and a decimeter. So let's try the two-step one as well. And I'll just set that up. So we'll start with 37. And so again, we'll do this two-step. So we want to go decimeters to meters to millimeters. And so if I want to go to meters, so 1 meter is 10 decimeters. And then I want to go from meters back to millimeters. So 1 meter is 1,000 millimeters. There again, we can see, right, our factor of 100 now between them. So, right, 1,000 divided by 10 gives us that 100 factor back to where we were. And then, of course, right, again, you can always just, as long as you can set this up, you know your units cancel, right? Decimeters, decimeters, meters, meters, leaving us with millimeters. Again, depending on your comfort level, so we can also just plug this into the calculator. So divided by 10 times 1,000, and we get our answer again. Questions on this one? So don't be shy to ask questions. And does anyone put this last one on the board? So this could be another tricky one. Again, depending on how you see it, you could go centimeters, meters to millimeters. So write your base unit. I said that's always your safe space. We have our conversion factors to get to our safe space, essentially. So you could always get there. Or you could do it directly if you know how many millimeters are in a centimeter. You could also look at, this is 10 to the negative 2, 10 to the negative 3. There's your factor of 10 difference. Let's see, so we have 0.002 centimeters. And so my only criticism is you put it over 1 centimeter, but you just want to do it over 1. Otherwise, the units cancel and give you, yeah.
I don't write it in that format, so I was like,
And then, but we have, so 10 millimeters is in 1 centimeter. So 0.02 centimeters. Again, I'll write out the 2-step conversion just in case people like that. So if you go centimeters, then we want to go to meters. And then from meters back to millimeters. And again, you can see that factor of 10, so right divided by 100 gives you times 10 here. So same answer. Oops, I wrote the wrong unit though, my answer. So just make sure you label your answers properly, unlike myself. So are we all feeling okay with that? Are we still struggling with dimensional analysis? I see some people might still be struggling. I wanted to show one other method, but I don't know. It's going to confuse people. Because the other thing that I was thinking about, if people are kind of struggling with this, some people may feel better if they do it in like a proportion way. Are y'all comfortable with proportions, especially like back there? Because you said y'all were struggling, kind of in that corner. So let's redo this one. So the 2.5 meters to millimeters in a proportion. And if you're totally confused, you can just tell me, and I'll forget we ever said that. So 2.5. So I'll say using proportions. So we wanted to go from 2.5 meters to millimeters. And so basically, right, what your conversion factor is just giving you a relationship. So maybe you've seen it another way. So again, kind of from our conversion factor, we know we have 1,000 millimeters in 1 meter. And so you could set it up as a proportion. And so proportion, if you remember, you just keep everything with like the same units consistent. So now if we're trying to get millimeters, solve for x. And then you could put 2.5 there. And then cross, multiply, and divide. Does this look familiar to anybody? So this would also give you that answer. So I'll just, do it. So that's 2.5 times 1,000. And of course, right, you would divide by 1, but divided by 1. So that does still give you the same answer, right? 2,500 millimeters. So that might be another way to think about these types of problems, is using a proportion. So I still think dimensional analysis is the best thing, because especially as we do like stoichiometry and kind of combine steps. But if you need to do it another way and kind of lay out step by step differently, this might be a good alternative. Any thoughts, feelings?
I like that way a lot better.
So you like proportions, so proportions make sense. So the only tricky part then if you use proportions is, you know, if you're totally comfortable, you could write your new conversion factor right with this, as long as you can figure out the difference between them using the exponents. All right, we'll probably move on for now, but just keep this, again, kind of in our back pocket of proportions. Potentially, if the dimensional analysis is not clicking, proportions might click better. All right, but let's go over, because we want to at least continue and figure out how to do the math. So I know everybody's now been in lab, so we've kind of gotten a taste for this. And y'all did pretty good on the labs that I saw. I just did a few minor corrections on everyone. Again, excellent job. And so now we got a sense in lab too of like, what does it mean to have things be only so accurate in lab, right? We have our rulers, we have different limitations. And so when we report our sig figs, right, it's dependent on our measured value. So again, you saw in lab, right, the balance only goes out to so many digits. And you can get a more expensive analytical balance, and that'll go out to one more digit. You could use like CalPERS, right, and that would give you a much more precision value, and then you would port all those values if you were using like an electronic CalPER. So it just all depends on how precise your glassware is. You also saw that, right, with like the Erlenmeyers. They're not very accurate. Even if you were to measure it like to the 50 and pour it into your graduated, it wouldn't match. And so it's all, again, dependent on the precision. And so the first part, before we like dive into the math, is just anytime we convert, it's always treated as an exact value. And you know, you want to report every digit that you're given in the conversion factors, just like you've been doing. And if you were to see this in any other cases, like with weirder numbers, like inches to centimeters, you just ignore these when calculating your sig figs. So, right, the sig figs would not drop to 1 based upon that. That would, so it's just based upon your measured value. And so let's look at kind of our rules then for sig figs, and then we'll look at how to do the math. So all non-zero values are significant. That makes sense, right? Anything you see, you want to write down. And so this number 536, that would have 3 sig figs. And then the next one is also fairly simple. So I call this our captive zero rule. So a 0 that's between any non-zero digits is significant. Again, that makes sense. So we have this number 6,703. Yes, that 0 is still significant. We know we can report accurately to all 4 of those digits here. And so now we look at the next 2 rules. I always call these our kind of order of magnitude, or let's say magnitude rules. So again, they're showing how big or small. And so let's look at that. So it says leading zeros. So placeholder zeros to the left of a non-zero digit are not significant. And so we're looking at this, so 0.0043, so only the last 2 digits are significant. And so, right, this is just showing how small. And another way to think about this is, can I rewrite this to get rid of the zeros and then show, right, that it really just has 2 sig figs? And of course, we could rewrite this as 4.3 times 10 to the -3rd. And so, right, this clearly shows there's only 2 sig figs. Again, those zeros just showing how small. And then, so the next one is pretty similar. except now it's showing how big. So it says zeros to the right after a non-zero digit are not significant. So looking at this number 7,000, so this is not showing any accuracy in this measurement. And so that's only 1 sig fig. So all these, right, are just showing how big. And so same thing with this next one, so 32,040. So these first 4, right, they are significant. Since they are numbers, right, we have a captive 0 in there. But then this last 0 is again just showing how big. And then our last one shows us an accuracy. And this is where students usually forget the zeros in their measurements. So that's what I was saying, right? If it's exactly on the line, you want to report 2 after to show, yes, my glassware is that accurate. And so zeros to the right after a decimal point are significant. So 50.0, that's 3 sig figs. And of course, right, that interior 0 is now significant since we put 1 after it. And then in this example, so 0.0600, so of course the first one just shows how small, so that's not significant. But then these 3, right, this shows accuracy. So whatever we were using, if we were using a balance, right, it went out that many digits and it was 0, 0, we know that accurately. And so again, I think you got a good taste of this in lab, and so you always want to estimate 1 after your markings. And so in lab, what would we measure this as? So you can, somebody give me an idea. What did somebody say? 4.55. So 4.55, so that would be perfect. And right, again, this last digit, like you practiced in lab today, it's uncertain, so we can all have different numbers there, potentially. And there was, I saw it in somebody's like post question thing, that extra question. So at least slightly mention, so with what defines whether something, right, whether we measure to the bottom of the meniscus or the top, that depends on the intermolecular forces. And so in this case, right, we have a little bit of it creeping up of the water hanging onto the side. So, right, some capillary action and molecular forces. So that's what causes water to do that concave behavior there. And then that's why you measure to the bottom of that meniscus. But then if you were to measure, look at another substance like mercury, for instance. So mercury is a little different. So it adheres more to itself than the sides of the glass, so opposed to water where it's adhering to the glass a little bit more strongly than itself. So mercury actually is convex, so you would measure that one to the top of its little convex thing. But you probably won't deal with mercury. Everyone's so scared of mercury, even though elemental mercury is actually not that bad. It just got a very bad reputation. All right, let's do a little practice. So take a minute or two, just kind of write down or think about what you think the sig figs are, and then we'll go over them as a class real quick. All right, let's start going over them. So just show me with your fingers. So how many sig figs are in this first one? Excellent. I see 2s everywhere, so very good. So all those zeros were just how big. And then so what about number 2? I see a bunch of 3s everywhere. Excellent. And what about this next one, number 3 here? So 3s again, some 3s. So don't forget, right, this last 0 is significant, so it's showing how accurate there. What about number 4? How many? So 2s, lots of 2s, very good. And then what about the last one? This one's a little tricky. I see some 2s. So it is indeed 2. So this is a weird case, and so you don't often see this, but sometimes, right, you may get a scenario like, let's say you want to write the number 100, but you want to show that all 3 are significant, right? Need to show. So there's a couple of ways to do that. And so putting a decimal after the 0, so that makes it, that shows, right, that this is significant. But honestly, this is kind of ambiguous, and if you were to see this in text, you might miss it. So it's not often used. So this shows 3 sig figs. And so it's better to write it in scientific notation. So 1.00, right, times 10 to the 2. So now this clearly shows, since we bothered to write zeros after the decimal point, so now we know all these 3 are significant. Or let's say, what if we were trying to write 100, but we only had 2 sig figs from accuracy? Again, same thing, we could write 1.0 now, times 10 to the 2. And so we know, right, well, that's really 100, but I'm showing that it has 2 sig figs. And then, so again, back to this number 5, it might be better to write it as 1.0 times 10 to the 1. So again, that it's very clear that there are 2 sig figs for that answer. But I wanted you to at least be aware of this little decimal point. Sometimes it does crop up in textbooks or something you see. Excellent. Any questions about that? Look like most people have that down. And so now let's figure out how to do the math. And I think a lot of you were kind of figuring this out, at least from your answers. It looked pretty good. Let's go over it formally. And so addition and subtraction, multiplication and division are the easier ones to do. And so all it is the least precise measured value determines the number of sig figs. So right, you just do your math and then you look back, okay, well if I was plugging in something with 2 sig figs and 3 sig figs, I need to only report to 2. So it's always the least number. And you just round appropriately. Addition and subtraction, it can get a little trickier in my opinion, only because I feel like you have to set it up elementary school style and you're just comparing the accuracy to after the decimal point. But we'll look at some examples and I think that'll be clearer. So now looking at this multiplication and division, and this is also a good reminder as to why you want to write down every digit that you have that your glassware gives you, because then you might end up in this awkward scenario. So we're trying to find some area. So we have 3.56 centimeters times 4. And so I'll plug it into the calculator just so we can follow along. And so, right, the calculator spits out 14.24, except we only have 1 sig fig here. Right, obviously this is 3, but we are limited by this one. So now we have to round this 14.24 all the way back down to 10. So that's, yeah, it feels a little uncomfortable. That's why, right, we want to measure more accurately so we can give a good answer. And so now same thing, so now let's try this one and look at the calculator. So 2.050. times 5. And so again, we're limited by this one to 2 sig figs. And so now we have to round, and this is where we get that awkward, right, 10 scenario, or they said, potentially write it in scientific notation to remove ambiguity. So same thing, right, in this example, again, only 1 sig fig, so that's our limit, so we had to round down, or round and chop off any decimal points. And so now looking at this one, don't let all this confuse you, right? So this is just conversion factor, conversion factor, conversion factor. So none of this counts. So then we just need to look at our initial number. And so we were started off with 2 sig figs. Again, conversion factors don't matter. So then we just need to report to 2 sig figs. And then, so addition, subtraction, like I said, feels like we got to set it up elementary school style to kind of help us out. And so now doing our math here. And so you look at the one that has the fewest after the decimal point. So in this case, we only went out to 2 after the decimal point, so that's as far as we can report. And then, so of course, in this case, we round up to 336.68 inches there. And so again, this is another what I call awkward scenario. So we don't have a lot of accuracy, right? We reported to none after the decimal point in this first value. So now you do the subtraction, you end up with this number, except we can only report to 56 centimeters, since we can't include anything after the decimal point. So this just rounds, again, down. Questions about this? And then, are we comfortable with scientific notation? I kind of have this here, just kind of as a reference. Again, just making sure we're all on the same page, since I don't know everyone's background. It's week 1 here. But it seems like we're okay with this. Again, if you're not and you're being shy, you can always talk to me later. But we can see, right, positive exponents, you just add numbers after the decimal point. And of course, negative is small. So you can just see how that's done. All right, let's look at some temperature scales. And so I'm sure people are familiar with the Fahrenheit scale. So of course, water freezes at 32 degrees Fahrenheit. Water boils at 212. And so notice that's really awkward. So that's 180 degrees difference between the freezing and boiling point. And so now if we look at Celsius and Kelvin, so they're a lot nicer. And so kind of the key that we notice right away is that the degree difference goes up the same, so meaning there's 100 degrees difference between freezing and boiling for Celsius, same thing for Kelvin. So does anybody know what the Kelvin scale is based off of? I can give another hint too, because there's this little value here. What does that mean, absolute 0? Anybody know? So absolute 0, this is kind of a theoretical point. So this means complete absence of molecular motion. Right, so we're kind of aware that, again, atoms are always vibrating, moving. We kind of mentioned that with the solids, right? We said even though they're a solid, right, the atoms are still vibrating. That electron is still running around the atom. But then if we could get to absolute zero, so again, this is a theoretical point, that would be the complete absence of molecular motion. So that's what we define as absolute zero. So that's what our scale is based upon. And so this is important too. So when we do like calculations later on down the line, like in pressure, I'm trying to think what else we do in this class. So we don't do too much like thermodynamic relevant stuff in here, you know, just basic introductory chemistry. But that's why we need to be in Kelvin, is because this has actually thermodynamic relevance. And of course, it goes starting at 0 to positive, whereas Celsius goes negative, so that causes some issues. That's why we have our Kelvin scale there. And so I'll put, here's at least, so this is kind of old now. I would have to look at what the latest is. So this is now 2003. But at MIT, they were kind of working on this. So they've gotten really, really close. So apparently now they're at 500 picokelvin, so almost to zero. I mean, that's honestly insane. But you could just see they have to do a lot of different things to isolate it. So they have apparently magnetic fields to kind of stop motion. So they're really just trying to stop molecular motion to get to this theoretical point. It's kind of interesting. Anyways, that's just where the research field is. So let's look at how we convert. And so we can say that our temperature Kelvin is equal to our temperature Celsius plus 273. And sometimes you see this written as 273.15. But honestly, I never use this 0.15 because if you look at your scales, especially in lab, right, if you're looking at your thermometer, it's not going to be that accurate. So I usually just abbreviate it to 273 there. And so then for converting Fahrenheit to Celsius, that could be a little trickier, but for y'all, I don't expect you to memorize these formulas or anything. We just want to be able to plug that in. So if we start with Celsius, that means we want to use this formula to get to Fahrenheit. So plugging our temperature Celsius in there, and of course times 9/5, which is also 1.8. So you might see 1.8 in other formulas. And then if you want to go from Fahrenheit to Celsius, just obviously watch your order of operations. So you need to do the subtraction first, and then you can multiply it by the 5/9. But again, I would provide this formula or something similar where you're just plugging it in on an exam. And so there's just our temperature conversion again. But again, exams are usually open note anyways. All right, let's look at some more stuff. And so density is a really important property. So you measure that in lab, actually, either today on Monday, you calculated density. It's a good way to sometimes identify objects. And so all density is a ratio of mass to volume. And so usually we see either grams per milliliter, or sometimes you see grams per centimeter cubed. And so 1 centimeter cubed is equal to 1 milliliter. And then just be prepared for other units. Not that we'll see them in here, but you could have like kilograms per meter cubed or any sort of different combinations, as long as it's a mass to volume ratio. So let's try the first example here. So we have 73.2 milliliters of a liquid. It has a mass of 61.5 grams. So what is the density? So this one's pretty straightforward. And so double check your sanity with your units and density. The units kind of give away what you have to do, right? It's grams over milliliters. So let's just plug that in. And again, that was following with the definition, density equals mass over volume. So what do we get for an answer? 0.84, and then let's tack a 0 on there because we have our 3 sig figs, so grams per milliliters. Excellent. So before we try this next one, are people familiar with the triangle trick? So when you have something that is written like this, you can rewrite it in what I call the triangle trick. So M goes on top, then we have dV on bottom. And so the triangle trick is just, right, you cover up whatever you're looking for. So we'll cover up density. Oh, that gives us mass divided by volume. So let's say you want to find mass, right? So cover mass up. Oh, now that's density times volume. But then, right, double check yourself. So mass equals density times our volume. Well, density is given in grams per milliliter times my volume. So yes, that would give me, right, a mass unit. So you can use both the triangle trick and your unit canceling dimensional analysis to kind of help you out. And so, right, same thing. Let's say you want volume, cover volume up. Well, that gives me mass divided by density. And then again, check that out with your units. So volume equals mass over density. Well, checking out my units, so that's grams. And then density, right? So density we said was grams per milliliter. So if you divide by that, milliliter goes on top, grams on bottom, giving us milliliters back out, just like we expected. So hopefully that helps. And again, there's always the triangle trick if you're still lost with these units. So looking at all this, see if you can solve this problem, and then we'll go through the class surveying A, B, C, D, E. So determine the volume of an object that has a mass of 455.6 grams and a density of 19.3 grams per centimeter cubed. See, we're getting answers. Be ready? All right, let's survey. Who thinks A? Any hands? B, C, D. All right, everybody likes D. So that is correct. And E. So excellent. So that was D. And so easy way, just cover volume. So then we needed to do mass divided by density. And it looks like most people got that. Excellent. Any questions on that one? And so one other little thing, so this is in your textbook, and so it might come up in definition. And so your textbook has specific gravity is just defined as, well, actually there's kind of two definitions. So I think your textbook has a more general definition of specific gravity. So specific gravity is really just a comparison of densities. But then what's kind of weirder is usually it's always done with water. And so water, though, has a density, right, of 1 gram per milliliter, or just 1. And so let's just take an example. And so let's look up hexane. So we can look at a substance, figure out its density. So its density of hexane is 0.6606 grams per milliliter. So hexane. And then so if we were to say, well, what's the specific gravity of hexane? Again, usually that's in reference compared to water, and it seems kind of silly and trivial, but again, at least we'll go over the definition. So then we want to compare it to water, so obviously that's just 0.66 grams per milliliter divided by 1 gram per milliliter. So the key thing about specific gravity is it is unitless, since it's a comparison of ratios. And so then, right, our specific gravity for hexane is just 0.66 then. So kind of silly, but at least we know it is by definition. All right. So we're kind of out of time for now, or at least with how I like to structure classes. So normally how our Wednesdays will work is we'll do about an hour of lecture. You know, in this case, I took 10 minutes more of your time, and then I would give you a 10-minute break, and then we would do our weekly quiz. So I still have, right, our welcome assignment, so I'll probably do that. But before we moved on, I didn't know if people wanted to do any more practice problems first, or if you just want to take a break, do our quiz, and then get individual help after the quiz. So are we ready to move on to quiz time? All right, so let's just take a 10-minute break for formality's sake. And like I said, this is just a welcome assignment quiz, so nothing difficult, so nothing to stress out about. But yeah, let's just take 10-minute breaks. That's going to be our general format, so I just want to practice that. And then I'll officially start our welcome quiz at 2:10 then. And so how it works, again, once you're done with the quiz, then you can just leave, or you can, take the rest of the time to ask questions. And I officially have office hours after anyways, so again, you can just, take that time to get your questions answered or work on homework, whatever you need to do. Recitation's kind of like your time to do stuff. All right, I will stop this stream, we'll take our break, and then we'll do our quiz.